And I'm like,
we're going live. Hey everyone, it is Hugo Bowne-Anderson here, and I am here with Jacopo Tagliabue. Hey there, Jacopo.
Hi.
We are so excited. Just 1 second, I'm sorry, I've got my own voice coming in my ears. We are so excited to be here today to have our first live coding session on how to build a full stack recommender system using Metaflow, among many other tools. If you could introduce yourself in the chat, we're going to wait a couple more minutes for people to roll on in. Let us know where you're calling in from, who you are, and what your interest in machine learning, data science, full stack recommender systems is and are. I'm here in Sydney, Australia, and Jacopo, you are in Brooklyn, New York City. Is that correct?
Correct.
Fantastic. And we're just really excited to be here. So introduce yourself in the chat as a few more people roll on in, and then we'll get started in a couple of minutes. Oh, this is great. Patrick Orlando from Sydney, Australia, working on RecSys and personalization. Fantastic. Good to have you here. And we have Syed Ahmed from NYC, studying computer science at NYU. And you've been teaching these types of things at NYU, haven't you, Jacopo?
Yes. Actually, the introduction to recommender system I'm going to go through today is also part of my class in ML system at NYU, where I teach at the Tandon School of Engineering. So.
Fantastic. Cool. And so we'll just wait 1 more minute for people to come on in. And once again, feel free to introduce yourself in the chat. That'd be fantastic. We also had a question at the start from Hung Bui. Will the video still be here after the live stream? Absolutely. This video will stay on our YouTube channel in perpetuity. So feel free to watch it daily. We also have the Saddle Point is calling in, and it's wow, 4:30 a.m. So thank you so much for joining. And that's actually Soma Davala from Wani AI. Who uses Metaflow. Fantastic. And Jacopo, you'll be happy to know Patrick Orlando recently saw a talk from Jacopo about ANN search in Lucene, and it was really great. And he's looking forward to this. We also have Tiago from Luiza Labs in the RecSys squad in Brazil. So we have a lot of representation from all around the world, and of course, hey Renee from NVIDIA Merlin team, who we're working with as well. And there's a lot of vibe going back and forth in the chat. So I think without further ado, we really should jump on in. So let's share our videos. Jacopo. Hey man.
Can you see me? Awesome.
I can. And you can see me, I hope?
Yeah. I still have this boomer moment with Zoom. I don't know why. I don't know why I'm so bad with it. I should have learned by now. But yeah.
So, Jacopo, you're a RecSys expert, former director of AI at Coveo. You're working on very exciting things, secret things at the moment. But we're here to dive into how to build a production-grade recommender system.
Absolutely, and look forward to spend the next hour together. Ask any question. No question is too too simple or is out of scope. Well, there are some questions out of scope, but you know what I mean. Just feel free to ask anything about what me and Hugo I'm gonna go through today, and we're gonna talk about a lot of open source tools. There's a lot of ground to cover, but hopefully we'll give you a good sense of what can be achieved thanks to the current MLOps ecosystem, even by a very small team, very few people. They can actually do great things that 5 years ago would have been impossible.
Exactly. And if you do want to code along, which I hope you do, I invite you to click on this link, which it's bit.ly/RecSys dash code along. I've included it in the YouTube chat as well. And I'm just going to give a brief tour of what we're actually doing there. So to do that, I need to share another browser. Can you see my Chrome?
I can see Chrome with sandboxes ready. Yes.
Fantastic. So if you go to that link, it will tell you to, it'll say, I'd like to provision a sandbox. You'll need to authenticate using Google or GitHub if you haven't done so already. But what we actually have here, which I'm super excited about, you may recognize this as looking like VS Code. We've built custom extensions on top of VS Code in your browser. I really think of it as like a superpowered version of VS Code because I get to use it for so many amazing things. But essentially, you require no setup today. What you get to do with us is to build a neural network sequential recommender system, end-to-end, production grade in the browser, doing all the modeling stuff that you like using Metaflow, which we'll introduce. And we've dealt with all the infrastructure for you. And that's one of the kind of value propositions of Metaflow, in my opinion, is it allows data scientists and ML engineers to focus on the top parts of the stack, being model building, feature engineering, all of these types of things, while having all the compute data orchestration as easily accessible as possible without having to worry about YAMLs, for example, right? And we'll see how that works today. But what we have is we have notebooks in here, and we'll see how we can do exploratory data analysis in notebooks. We've got our scripts where we write our machine learning workflows. We have another notebook where we're able to analyze and check out all the machine learning flows we've done already that have run. And that's another thing that may excite you if you don't know about Metaflow. I kind of think of it like a video game in some ways, where you get to, you save a snapshot of a video game and you can go back to that point. In Metaflow, every machine learning flow you run is saved. We're doing that in S3 currently, but all metadata associated with any flow is saved, so we can go and analyze and go through all our flows, and then, for example, promote a challenger model to production or whatever it is, right? And then at the end, we'll be making some real-time predictions, which is super exciting. I do want to just check in on the chat. Could you let us know if that link didn't work for you, or if it did? That would be useful. I presume it worked for most, but give me a thumbs up or say, hey, it worked. If it didn't work or something's up, let us know as well. Maybe a slight bit more of introduction of how we think about what data scientists do. This is, and I show this because I really, this mental model of what data scientists do, I'm a big fan of. But on top of that, I love what my team has done in terms of design principles here. We have our little purple hat data scientists there. At their laptop, their job is to build applications that leverage data, statistics, and ML. They need to access data wherever it is. If it's in the cloud, data lakes, data warehouses, it doesn't, on average, occur locally, right? They need orchestration to orchestrate complex workflows. They need to have data go back and forth between orchestration and their local workstation as well. Versioning is required of code, data, and models, so not just code. They also require access to compute, whether that's Kubernetes clusters, which are configured for them, and Metaflow has an @Kubernetes decorator, which we won't explore today, but you can check out, which allows you to intuitively and easily access Kubernetes clusters. And we're required to push stuff to deploy stuff as well, right? So there are a lot of moving parts here. And that's what we really try to help data scientists work with using Metaflow. But this sandbox, what we want to do is set up all the infrastructure so that you can build your end-to-end systems immediately in our sandbox as well. So you can kind of think of it as a Google Colab for MLOps or something along those lines, okay? So perhaps without further ado, I will, and a lot of people in the chat are saying it's working fine. Kazi Saad has a great question. The linked work, but can we reuse something similar when building our own use case? The answer is yes, but with I suppose the constraint that it is not actually intended for production use. We will show how you can deploy an endpoint in it today, But when building stuff in prod, or making production workflows, that's not the intention. This is really for educational purposes. But if you're interested in something similar that can be used for production use cases, I would, and this is a shameless plug, but I'd have to fire myself were I to not, I don't even know if I'm allowed to do that. Were I not to say this, I mean, we have just announced our Outerbounds platform, which is essentially the type of thing that you're looking for. So I've linked to a blog post there if you're interested. But without further ado, Jacopo, I would love for you to take the floor and share your screen, and we can go through the agenda and then really jump in.
So let me see. Oh, I have screen sharing disabled. So
of course. I will make you the co-host. There we go.
Thank you. I just got promoted. That's so good. Cool. Also, I have to say, today we're gonna see many incredible things. One of the most incredible thing happened in the beginning when Hugo actually got my last name almost right, which is almost impossible for people to do. So, 10 points to Hugo already.
Fantastic. Thank you.
Yeah. If you want in the chat to send a vocal message, or anybody wants to try and repeat the stunt, we're going to give you 10 points as well. Free Metaflow for 1 year. No, I'm kidding. I'm not allowed to do this. So let me share this. Can you see my screen? Hopefully
absolutely.
You can. Okay. So today, simple agenda. We already did the Metaflow sandbox, so awesome. We are gonna go and just bear with me for literally the next hopefully 7 to 10 minutes most. We're gonna just have a small overview of recommender system, and then we're gonna discuss the data set in the pipeline that actually we built, and is the one that we're actually gonna code together. Meaning that if you're already in the Metaflow sandbox, we're gonna go through the steps in our tutorial, and we're gonna do them together and comment what we believe are the most salient part by running the code with you. Again, if you have any question of any sort and type, please do not hesitate to ask. One quick point about today, while we're actually gonna train a model, and this model is pretty powerful, and I'm happy to point to literature in case you want to go dive deeper into that. Today, the focus is about tooling and the end-to-end experience. So we're going to work with a smaller data set than the one that you can actually find online, okay? So that it can actually be much faster when we try it out. And we're not going to spend a tons of time discussing the model itself. But if you have questions about the model, happy to take them at the very end, okay? So let's see what we're doing today. So this, in a picture, is a flow is worth 1,000 words. So this is what we're going to build, okay? So going from the left to the right, from raw data, imagine in a real use case, the data that your company has, and for your data science workflow. And to the right, we're gonna go from raw data to actually deploying. Okay, the tutorial on the website has a full-fledged deployment with SageMaker. We're gonna stop just one tiny step before today. We're going to deploy a local endpoint in a sandbox so that we can play around without spending basically cloud money. But the same exact logic applies to cloud deployment, okay? So we're literally going to go to the full cycle of an ML project, building recommender system that start from data about what people see. In this case, it's going to be playlist that, people listen to a recommender system that, given a set of songs, you're going to suggest new songs to us, okay? And we're going to see, in several iterations how that is actually unfolding, okay? So without pretending to substitute for, one of the biggest field of machine learning, which is recommender system, I just want to make, a bit of an introduction about what we mean about building a recommender system, why recommender systems are important. And I will try to convey. So if you're in the field, I know Rona is here, so I know there are experts here that can actually correct me. But if you're new to the field, I will try to convey what I believe is the most fundamental insight about recommender system, which will be enough to understand what we're building today. Again, you can get a PhD in this topic, so we're not going to try and exhaust it. What is a recommender system? Well, everybody knows what a recommender system is because we're constantly interacting with them, right? Amazon suggests you every day what you should book what you should read as a book. Netflix suggests you every day what movies you should watch. LinkedIn may suggest you, for example, to add me or Hugo because you liked our post about this live coding event, right? So recommender system are basically machine learning system. They're probably the most ubiquitous one. They try to predict what you're gonna like based on what you liked in the past, okay? There's a million ways in which you build a recommender system, but generically speaking, there's always, an input, which can be, for example, a user, like in the Netflix case, and there's gonna be an output, which, again, in the Netflix case, is a set of movies that Netflix thinks Jacopo may like based on what I liked in the past. The key intuition, which is very, very important, is this one. With some caveat, but most recommender systems are based on this fundamental idea. If you like something in the past, you're gonna likely to like things that are similar to that in the future as well, okay? For example, I'm a huge fan of, adult comic shows, like the animation show, like the one that you saw there. And so Netflix thinks that since I saw some of them before, I don't know, Disenchanted, for example, or Rick and Morty, I'm a huge fan of Rick and Morty, this is something I would like as well. So I would actually like to watch BoJack Horseman as well, okay? And this intuition is at play in any recommender system that you have. When Amazon suggests you a book, it's because they think this book is sufficiently similar to what you just read. Or when LinkedIn suggests you a person to follow, it's because you may have the same interest. Okay, that's kind of the general idea.
And I just want to add to that it's similarity, and we'll get to what some definition of similarity is, but that's going to be key. But it also, so I'll give a counter example of something that's similar that didn't work for me, where I bought several years ago a battery pack on Amazon, and it was black. And the next day, Amazon suggested that maybe I want a red battery pack. Now that's similar, right? But I've just bought a battery pack, so I likely don't want another one immediately, right?
Yeah, I mean, that's a fantastic example. We are actually going to see a similar example today with songs that are like near duplicates. So songs that are actually similar, but not in a good way. But this, even if Amazon makes a mistake, it means that this is a very hard problem, as you can probably guess. So building a recommender system that actually works is a very, very hard and definitely unsolved problem. But I think in the last 5 years, what we came to realize is that we're now in a much better position to at least solve the basic use cases with open source.
Absolutely.
But yes, there's still things that we don't know how to fix.
Yeah, and the other thing, actually, and I know this is kind of putting the cart before the horse in some ways, but in a business sense, if Amazon recommends 10 things to me after I buy something, all they need is for me to click on one as well, right? So if they've got a whole bunch of ads based on stuff that I bought in the past, there's a lot of low-hanging fruit there in some ways.
Yes, and there's different ways in which you can also make something more appealing, by, for example, comparing with something that they know is least appealing, right? When you build a recommender system at that scale, it becomes important not to just understand what you would like, Hugo, but also what Amazon would like you to buy. Meaning, what is the product with the highest margin? What do they make profit on, and so on and so forth. Which, of course, we're not going to go into this level of details, but it's important to understand the basics of how the flow works to then go over it again and kind of like innovate in this sense.
Yep. Absolutely.
So let me, does it change? Yes. So let me go a bit deeper into this intuition about what does it mean similar, okay? And I swear this is the, basically the last boring theoretical concept of today, okay? So I pick here some movies and I manually place them along two axes in this space, right? One is the violence axis and one is the action axis. And these are three movies that I like there's Die Hard, there's Indiana Jones, and Fast and Furious, which means that I'm very old, to be able to actually remember all of this. And I'm sure Hugo remembers some of them as well.
Absolutely fantastic movies.
Yeah. So the observation here, like the first observation is that you can think of movies in this space as, as point in this space, as vectors in 2 dimensions, right? So Indiana Jones is, like a lot of action, not so much violence, and Die Hard is a bit more action and maybe a lot of violence, okay? And the second observation is that once you put things into this space, things that are similar together tends to be, somehow closer in the space. Meaning, Indiana Jones and Fast and Furious are, in some sense, more similar to between them than with Die Hard, okay? And of course, the trick here is that Jacopo, as a human that already saw all these movies, pick a position in the space that made some sense, okay? While we're building a recommender system, this is not given. If this was given, we have nothing to do. So the job of a recommender system is basically learn, a position of the item in the space such that when things are close together, they're actually similar in some ways, okay? So consider like a simple recipe to build a recommender system. Let's say we're able to build a space like this one where movies are placed according to some logic. We're going to go through that, but it doesn't really matter now, okay? Now, let's say we have a user, Jacopo, okay? And let's say we can place Jacopo in the same space as the movies we have. How do we do that? For example, by placing Jacopo near the last movies that Jacopo saw. So Jacopo saw Lethal Weapon yesterday. Again, very, very 80s references here, okay? And so this is where Jacopo is in this space, okay? So how do we build a recommender out of this information? Well, we just get the closest movie in the space next to Jacopo, okay? Which in this case will be Die Hard because it's the closest movie next to Lethal Weapon. This is not, it may sound a bit of abstract, but it's not very different from what you do in the physical world. Like if one of your friends goes on vacation in Aspen, Colorado, and the other one goes in Maui, Hawaii, there's a lot you can tell about what they like just by their physical position in the geographical space, okay? This is similar, like recommender system are like GPS for preferences, okay? So you're not placing users on the earth, you're placing users on a space when they kind of can navigate depending on the preference they have. So you good? Do we have any question about this?
No, everything's clear. And so I do think people may, if they've just joined, feel free to ask questions in the chat and we'll get to them. But this is super clear. Beautiful explanation, Jacopo.
Awesome. So let's ask our question is, how do we learn, how do we map user and item to vectors? Remember, we're cheating here as Jacopo placed all these movies in a way that actually made sense in this space. But when we start over, we don't know how to do that. So let's go quickly on how to do that. And then we can go to the coding part of how we actually implement this flow, okay? So we're going to build a song recommender today. So we're going to build a recommender system, okay? That given, in particular, the start of a playlist on Spotify or Apple Music or whatever, it's going to suggest you what to listen to next, okay? You can imagine using this for building, I don't know, a personal ratio or to suggest how to complete a playlist that you want to continue based on something that you already know, okay? To do this, we're going to using a known dataset on playlist on Spotify that is releasing Creative Commons. You can download it. It's actually pre-built inside of our sandbox. So we don't have to do much today to start. But if you want to use the full one, please go ahead and do that on Kaggle. So what is it? What's our training idea? Our training idea, again, we're not going to go through that in details, but is that we're going to borrow a model from natural language processing. It's called word2vec. If you know what that is, awesome. All of this is going to become, immediately clear to you. If you don't know what it is, doesn't really matter in the details. The general intuition is as follows. Words that appear together in a sentence are very similar, okay? So if we can have a lot of sentences, we can learn basically which words are similar to each other just by co-occurrence patterns in some sense, right? This is the equivalent of the saying, you learn a lot of a man by the company he keeps, right? That's kind of the same idea. Like, so cat and dog are very similar words because they appear in very similar sentences. Now, take this intuition and applies that to song, right? So what we're going to assume here is that where song appears next to each other in a playlist is because people thought that these songs somehow are similar or are good together or they match, okay? And we're going to leverage this intuition to teach a machine learning system how to learn what is similar and what is not, okay? So when we go on and build our training loop, we're going to see that we're going to get as input a list of playlists, each containing n songs, okay? The length may differ. Some playlists may be 10 items. Some playlists may be 4 items, okay? And we're going to put them into this model, song2vec, which will output a space exactly like the movie space that we saw before. This is not going to be a movie space. It's going to be a song space. But the exact same intuition about the GPS will apply, meaning songs that are close together in this space are going to be similar. So when we need to recommend new song, what we're gonna do is very simple. We're gonna take a playlist at test time. We're gonna take the last song of that playlist. We're gonna go into the space and search what is the most similar song into that, and then we're gonna pick that as our recommendation. Again, nothing scary. It's exactly the same thing we did with movies. The only difference is that with movies, I handpick the space, while here, since we're doing machine learning, we're gonna learn the space based on our training set. And again, going back to our initial slide, this is how all the pieces fit together, okay? So we're gonna prepare the data set in a way that respects the training set that I just described. We're gonna use a library to train different, latent spaces that call embeddings, technically, different models. And then we're gonna pick the best one and then deploy that in some sense. So all good?
This is perfect. I'm so excited. And also, it's so great to see so many different open source tools used and interoperating to create a flow like this as well.
Yeah, I think a fantastic thing about the ecosystem and about ML that doesn't get praised enough is the abundance of incredible open source contribution that that literally powers everything we do. So, which I think we should really be grateful to all the companies, of course, Outerbounds, among them, that actually put a lot of effort into making our open source tooling as good as it is. Again, 5-6 years ago, all of this would have taken like a small army of machine learning engineers to be ready. And it's incredible that we can run this basically with one person. And today we're going to run it inside a browser without even installing anything.
It's incredible. Great.
So
I've included the link again. So maybe if you just go to the link, just so we can get the total flow going again.
Can you see this?
Yeah. So if you click on that,
okay,
copy and paste it, and just so everyone can. Great. So once again, for those who are doing this for the first time, you'll be asked to log in using Gmail or Google or GitHub, and it will say initialize a sandbox or something along those lines. Jacopo, welcome back, Jacopo, has already done this, so he can just click open my sandbox. So if you do that, Jacopo, or...
Oh, okay. I thought, okay.
Yep.
Because I already have it open on the other side. Yes.
Of course. And here we are. And for those who are just joining or weren't here when I introduced it, this essentially is a super powered version of VS Code, custom extensions on VS Code in your browser. You can see Jacopo has a notebook there. He has a terminal below. Jacopo, if you just click on lesson 2, the query faster with DuckDB, for example, you see we have scripts there. So essentially what we're able to do is build this end-to-end production grade workflow in your browser in VS Code without any setup on your part, which I'm so grateful and humbled to be working with the people I work to who create this type of stuff so that we can build this type of content together. It's really, I feel blessed. So perhaps having said all of that, without further ado, we can jump into the notebook.
Awesome. So I hope everybody is on the same page, like virtually, like conceptually, but also like literally here. Yep. And we can run all of this together. So in particular, as Hugo was saying, if this code, all of this is interactive and runs the actual code that there is. So when
you want to just minimize the terminal and the left-hand panel.
Sorry. Yes, I'm so used to this.
No, totally cool. And if you click the Metaflow button in the bottom left on the left hand, I think that may. Yes. So now we can see.
Okay. So awesome. So the notebook kind of like goes back to a bit of the things that we discussed. So we're not going to go through that again. What I just want to make sure that we understand is, how do we shape our data? Because it's going to be important in a way that makes sense for our model. Okay. Remember, the training set you see here is a list of playlists. For example, the first place is 3 songs, the second place is 6, the third place is 2, whatever. And the way in which we're gonna tackle this is we train latent space. Remember, like the movie thing, but for songs. And then at prediction time, we're gonna take a playlist. For example, this one, songs 5 to 5, song 22, blah, blah, blah. we're gonna cut the last one, okay, the last item in this playlist, and we're gonna use the previous items to predict the last item. This is how we're gonna evaluate this model, okay? And the intuition here is what? That the best model is a model which is gonna be able to complete the test playlist as better as possible, right? So the perfect model, a model that can basically literally read into your mind, would be able to obtain 100% accuracy on this, right? Because they'll always guess what is the next song in the playlist, okay? Of course, such a model is impossible. And again, today is not really about the quality of the model, but it's important to understand how we set up ourselves for success in a way that is measurable and reproducible, okay? Because we always need to know how our models are doing. We're gonna train different models today, and the fact that we have a quantitative way to distinguish between them is fundamental for us to being able to understand what's better and what's not, okay?
And is the fact that we're predicting the next one based on what's come before, is that why it's called sequential recommendations?
Exactly.
Okay.
So if you want the Google phrase to Google this is actually a case of sequential recommendation, because the input is a sequence and the output is basically the next event in the sequence, okay? And this is like a very modern way of approaching recommender system, okay? I mean, I don't want to spoil it, but there may be an event in the future, you know, on this very same channel, where we're gonna do a different and more complex model. But for now, we'll start for this, which is a fantastic start anyway. So let's see what our data set look like. You know, let's a good old exploratory data analysis. So the file here is been already in your sandbox. So when you run this, you don't have to download absolutely anything. And again, it's a shorter, smaller version of the entire data set. So let me actually do a bit more. Sorry. Let me actually make it as a bit bigger. Okay, awesome.
And I'm also going to link once again to the tutorial that this code along is based on our website, where you can access the entire, I mean, it's in this notebook as well, but you can access the entire data set and clean it yourself and that type of stuff as well.
So this is the data we're getting. Remember, our DAG, this is, left, like this is the leftmost part. This is where the data that we get from our business, in the case that we're running this for a company, okay? Each row here represents a track, right? A song. There's an artist, there's, an ID for the user, and there's a playlist here, right? You see here. So these users have built a playlist, which is called Hard Rock 2010, which contains 6 songs. And then the same user has built another playlist, which is called IOW, which I have no idea what that means. I don't know if that means anything in English, Hugo. Does it mean anything?
I'm not sure. I haven't seen it.
Okay. So no, because it's maybe one of these millennial thing that I don't understand. But no, so this whatever it means. But there's another playlist here. Maybe it's bigger actually. Let's see. Let's run this. Yes, see the continue. So there's another playlist which is bigger, which has other songs and so on. And remember, we're trying to predict playlist continuation. So the way in which we're gonna do that in the next step, we're gonna collapse all these rows into a list in such a way that then we can do exactly what we described. Takes the first, in this case, let's say the first. Can you see this? The first 5, and then the 6th one is gonna be our test. Okay. So let's inspect our data set. Standard pandas. There's like 1 million song here. These are not playlists. These are the total amount of songs. So the plays are much lower in cardinality. And we can actually inspect very easily, just standard Python, which are the top artists and the top songs that we have. So the top artist apparently is Daft Punk. The artist is most represented here. And these are the songs that appear actually the most in our...
And Jacopo, just quickly, Tiago Bueno from Brazil just commented, IOW is the Isle of Wight festival. So there we go.
Thank you very much. Thank you very much. The power,
crowdsourcing on YouTube.
Wisdom of the crowd. Yeah,
exactly.
Awesome. Nothing particularly surprising here. But what I want to show you before we go on the other side is that it's always good. Again, I'm sure I'm preaching to the choir here, being somehow the audience very experienced. But it's always good to have a look at our distribution of our variable because we actually build something. And once you actually do that, so once you plot the distribution of artists and songs, you're going to find out a phenomenon that is very, very common in most of recommender system, in general, most of online distribution. There is a very, very few number of artists is responsible for the vast majority of data points, right? And that's true of songs as well, right? In other words, everybody listens to Kanye West, right? But then there's like a random song of an unknown artist that has been included twice in the entire data set, right? And you can think about Netflix or Amazon, you can easily map that to your experience, right? There's like most people on Netflix watch 3 or 4 blockbusters, and then there are movies that almost nobody see. And imagine on Amazon has millions of books, right? Of course, everybody reads Harry Potter, but then there's like, probably more than 1 million books that have been bought, twice, 5 times, 10 times, and so on and so forth, right? This is important. We're not going to go through this that much, but because machine learning is at the end an exercise in fighting data sparsity, that's literally what learning is. The fact that our distribution are so power law-like is going to make much harder for the model to learn about people, to learn about artists and songs that are not popular. In other words, we expect the model to become very good at suggesting Beyonce and Kanye West, but the model is going to be not as good recommending song by Nada Surf, because I'm probably the only one here that knows about Nada Surf, like as of today. I don't know, maybe Hugo knows Nada Surf. I don't know.
I do not. No, but I'm excited to find out.
Proving my point. So
should we listen to some now? Oh no, that's probably not the best use of it. Yeah. Probably got a pretty high churn rate.
Yeah, exactly. So this is, it's a totally, safe for work kind of band. So I'm glad that I actually picked that as an example. So if you're really like a statistic nerds, we're also using a fantastic package here called Power Law that actually fits a Power Law into this, and it fits like pretty well. The dotted line is the theoretical Power Law. We're not going to go through this, but if you're a statistic nerd, I will strongly encourage you to go deeper into this and check this package, which again, it's open source and it's super cool. But that said,
if you're a half statistics nerd, a power law, if you plot on double log axes, will become linear, and that's why we're actually seeing a line there, which is super cool.
Sorry, fair point that I failed to mention.
No,
okay.
I mean that's what this is about. Riffing.
Okay. So remember what we're trying to do now. So we're trying to go from this representation, which is our file, okay, to our training and test set, right? This is the first thing we need to do to train a model, okay? And we're gonna do that. If you click on, the second step, we're gonna do that in Metaflow. So this is a typical Metaflow script. For those of you who are new or like super not experienced into this, you see that this is a standard Python file. No need to worry. No need to panic. It's just a special type of class. In particular, is a class that inherits the flow spec from here. You can see here, okay? And then we're gonna see something today that we're gonna see in all the iteration. That is, remember these steps here, all the nodes here in violet. This corresponds 1-to-1 to Python function that are decorated with the step here, okay? There's gonna be a start and an end one, which you can guess what they do. And then we go from one to the other by using the next special words, okay? So this says that the start is followed by the prepared dataset function, okay? And inside the function is standard Python. You can write whatever Python you want as if it's any other Python program. This is enough for Metaflow to understand how the steps are concatenated and to build the pipeline for you. Is that a good sum up?
That's a fantastic description. And I'll state maybe a couple more things. Metaflow is really agnostic with respect to how you write your flows. All Metaflow requires is that you have a start step and an end step. And then if you do some branching, you join in a way that actually makes sense. The other thing I want to note that Jacopo has done here is, he has a start step, then a prepared dataset step, and then what's the next one called?
These we just ends because we're just gonna do the first iteration now.
Yeah, exactly. So what we'll see is that we Jacopo will decouple certain bits of, computational and business logic from each other, so that you have a prepared data step set, then a train step, then a predict step, or whatever it is, right? So you can actually write flows that kind of mimic how our mental models of the steps in machine learning workflows as well. So there are some best practices to think through there.
Yeah, I think one of the coolest things that attracted me to Metaflow like a couple of years ago now, so it's been a while, is the fact that Metaflow enforced through what I call good abstraction, best practices in how you actually structure your product, right? Since it's basically invite you to divide your product in nodes, in computational nodes, like the one that you see here. It also kind of enforced this type of idea that, modularity is important, which I think is one of the most important pieces when building recommender system that actually works. So let me go back to this. Okay. Sorry, the Zoom bar is like on top of everything. Okay, so let's run this. So there are two ways you can run this. You see me down here. I'm doing Python. The name of this file is called data_flow. You can see here, and then run. Okay, I'm gonna press enter, and then while it runs, I'm gonna explain the other way to run it. Okay, the other way to run it is on the left here. There's a button called Run This Flow. Okay, which has been gently provided by Hugo, Eddie, and the team for you to just go quickly over, over this tutorial without actually writing anything. Okay, but if you want to have a real Metaflow experience, like if you want to see what actually would happen if you were to develop this for production, I will suggest you to use the command line like I just did. Okay, let me...
Amazing. And we actually have a great question. So the other thing that I think you've really clarified, but to just really drive this message home, you have flows in Python scripts, and then you can execute them from your terminal. Now we're doing it in VS Code, but it doesn't matter where, as long as you're executing from the terminal, analyze data, analyze flows, results of flows in notebooks, write flows in scripts, execute them in terminal. We have a great question from Massimiliano Vezzoli. So I can say Jacopo Tagliabue, and maybe both are close in terms of my pronunciation. I get close, but our friend here asks, compared to usual Python, I see you import packages within the class methods. Any reason for this? Jacopo.
Like here? Yes. Yeah. So this is a very good question. It is slightly subtle. It's slightly subtle. So we're not going to see that today, but one of the main features of Metaflow is the ability to run any step in different environment. So not just locally, in this case, locally to my sandbox, but also ship this very part of code, for example, to a GPU for executing, like, let's say, the training very fast. If you do that, you want to make sure that the GPU dependencies are as contained as possible, meaning that if you use, for example, TensorFlow, that actually appears only in the step where it's actually used, okay? To simplify the job of like sending stuff out and having less dependencies issue, okay? Yeah. So very good question. Is a bit of an advanced use cases. I just do this because I'm used to it. But yes, fantastic questions, and happy to go on that. And
the truth is, you can do your imports at an entire flow level or a step level. But we do encourage people for best practices to do it at a step level, unless it's being used in the entire flow. But specifically for that reason, if you had a big parallel training step and you wanted to send that to the cloud, and you only want PyTorch or TensorFlow up there, then you don't need it in your other steps, essentially.
Okay, so other questions or?
No, and Massimiliano responded, makes perfect sense. So, I mean.
Awesome. Thanks, Massimiliano. Also 10 out of 10 for me for pronunciation. So
you have a unfair advantage though.
That's fair. So I just want to show you what we discussed before. So we're using a fantastic open source thing called DuckDB. It's an in-memory database, means it's going to be a database that lives between line 29 and, well, basically, yes, line 86, okay? But it allows you to read directly from the Parquet file. You see here, the syntax, it's pretty straightforward. We literally read from here, from a Parquet like it's a table, if you're familiar with SQL, and then allows you to run very, very fast transformation using SQL, okay? If you're not comfortable with SQL, you can restructure the entire thing here with pandas, for example, if you like pandas, or rapids, or whatever you guys are using, or polars, okay? But I'm really comfortable with SQL, especially doing aggregation, and I find fantastic the fact that I can have an open source tool that is so fast and so easy to read, right? In particular, remember what we try to do, right? Remember, we have a list of songs, and we want to transform that into a data set where we have actually a sequence of songs from the same playlist, right? That's what we need to do. And you see here, we're gonna print it out like, like a one playlist, right? And this thing here corresponds to one row in our data set. And you can look here to understand what we're doing. So the first field is the playlist ID. Okay, perfect. And then you can see here there are sequence, right? So this is the sequence of the artist in this playlist, right? Followed by the sequence of the song in the very same playlist, okay? And if you look at the last field is the track test, meaning is the last track in this thing. You see here, so this is the last track, which is, of course, exactly the last track of this playlist, right? So this simple 6-line SQL query took our 1.5 million song in, I don't know, half a second, and prepared them in a data set that is ready for our model to be used, okay? So this is fantastic, and it scales pretty well. Like, the data set is small, but you'd be surprised, by how well how far you can go with this approach. The last thing I just want to say is that typical Metaflow stuff. So once we do the train, validate, and test plate, I guess everybody knows what they are. We're gonna use the fantastic self syntax of Metaflow to version that. What does it mean? It means that these artifacts are forever and ever stored as part of this flow in our data store. In this case is in AWS or wherever you define it to be. And these variables can be reused later on when we actually build a more complex flow.
This is actually an important point. I mean, all the points are important, but it's actually very important to be specific about if you were just to call it df_dataset, it would not be accessible in your next steps, right? So use the instance variable self dot in order to do that essentially. And as Jacopo very presciently made clear, it also stores it in all of your metadata. So when we want to analyze our results and have a look at what was happening in our flows, all of that metadata is, in this case, I mean, you can set up your Metaflow metadata wherever you want. In this case, it's all stored on S3, so we can access it very quickly in order to analyze the results of our flows after the fact.
Awesome. So let's go to build the recommender model now that everything is set up. Okay.
Amazing.
So you see here, we're gonna proceed in steps. So basically, we're expanding our initial flow, adding more and more steps to the pipeline to make it more and more complete. Remember, we need to build the entire thing. Okay. So there's a bunch more import here, but again, the most important thing is that we go from prepared dataset, which is what we just did, to, we're gonna see here, a new function, which is generate embeddings. Let's go and see what that does. The generate embeddings function, which is decorated with step, so again, is one of these functional nodes in the pipeline, okay? Use the word2vec model that we discussed to build our latent space, okay? So what we're doing here is that we're feeding the data set we just prepared to the word2vec model to get an embedding space, okay? And to get our first version of this model, okay? And once we did that, we're gonna evaluate this, okay? By how do we gonna do that? We're gonna do that as we explained, right? We're gonna feed the model some playlist that he hasn't seen. We're gonna cut the last song out like we did here, and we're gonna ask the model how good it is. Okay, this is called iterate. So we're just gonna count of how many predictions we make, how many actually are correct. Okay, we're gonna consider the model correct if the target item is in the top, I think is 100 in that. How do I know this? It's because I declared this, yes. So this is the parameter we're gonna use. So this is 100, okay? So let me run this. Now we're gonna press the button instead of running manually. So you're gonna see that it's exactly the same thing, okay? So I'm gonna press run this flow. There's some magic here in the sandbox to make sure that we run with the exact command. And now we're running here, okay? The first part, to prepare dataset, you're gonna see here is exactly the same as before. Okay, no new thing here. But what we're gonna see here is that how that actually becomes a model that is gonna be trained by our system. You see, the task is finished successful, and now we're starting training. Okay, it's a very small data set, so it's gonna take it's gonna take not that much time to actually do this. Okay, and we're gonna see here some printing, some stuff that I decide to print to help you understanding what's happening. Okay, you see here that every time there's a print here, you're gonna find it here, right? Vector space size, example track, and so on. Okay, so what we see here is we went from the raw data to the to our data set, to a first version of our model, and one measure of accuracy, which is this one, right? So in particular, on the test set, we're averaging 0.3 iterate for our current model.
And
Hugo, still making sense?
Yeah, absolutely. And is that hit rate any good, or?
Very good question. How do we know if this rate is any good or not? So it may be that in real context, you guys have a baseline, meaning that you already have a system in production with some numbers, and you know that numbers, you need to be better, or you need to be in the ballpark of that, okay? Or you're running maybe against a data set that many people have done research on, so you can go and look at the papers to understand what counts as a good model. But let's assume that this is the first time that you do this. So how do we know how good is this model? Well, the best way to do this is, and we go to number 4, is to train a bunch of models in parallel, okay, with different settings, and understand how good we can be just by changing those settings, okay? So we're gonna do that, and while I run this flow,
we have a couple of questions. Patrick has a good question. If your data's live and needs to be streamed from object storage, I imagine you'd use this differently?
Yes. So Metaflow, as it is for now, is mostly concerned about the training loop that happens. It can happen, on any schedule that you want. It can happen at every 5 minutes. It can happen every hour. It can happen every day. Actually, Metaflow automatically schedule things for you. We're not going to see this today, but this is a functionality that is actually right. So if you want to do streaming, meaning Flink or kind of like Apache Spark streaming kind of things, this pattern may not be the perfect one for you. In general, in my experience with recommender system, there's not such a need to do streaming training or like online training. You may have the need to do online serving. And in part, we're going to see how that works at the end of today.
Great. And we have one other question. Fabrizio Milo says, is there some magic that happens when you do self.df test equals test?
Oh, no. So awesome here. No, I'm just assigning the test that I built. This is a simple data frame that I built with the standard NumPy to a Metaflow version variable. Okay.
Yeah.
Because by doing this, then I can do here. There's going to be a self-test here. Okay. It's going to be a self-test. Yes. Oh, yes. There's going to be a df test here. Yes. Okay. That I can reuse. Okay. If I didn't do that, the variable will die inside of the Python function, like all the Python local variables you're familiar with. By assigning that to the class that encapsulate all the steps, I'm able to reference that variable across all the steps, which is particularly useful for datasets.
Yeah, exactly. And so Patrick has now clarified. He says, sorry, not streaming training, more data that can't fit in memory. Self.train equals train would not be the actual data.
Oh, fantastic. Okay, that's a very good point. So
yeah. So would it just be a reference to the location in object storage?
Exactly. So you can do, so there's a bunch of things you can do there. So one is Metaflow actually is an S3 optimized client. So you'll be surprised by how fast actually it is to even send, tens of gigabytes to S3 and reading them back. So that's point number one. So unless we're talking data in the terabyte scale, again, there's a lot of things that you can get out of this setting before actually worrying about something else. On the other side, if your data set is really humongous, okay, for example, it sits in Snowflake or in a distributed, engine, it may not make sense to, snapshot it back to your data store just because it's going to be too big. So you can just store whatever pointer to the actual data set that you generate in some sense, so that you can actually have a version in that sense. General suggestion is just buy a big box.
Yeah.
Like avoid distributed system as long as you can, because in many cases the marginal value doesn't really justify the incredible additional cost in maintenance that you incur into that.
So let's tune, dude.
Okay, awesome. So I just wanted to show one thing about this. So while we were discussing, thanks so much for the question. I launched this flow, which maybe you guys launched as well from YouTube. And you see here that now we don't have one iterate, we have three, right? Why? What happens? Well, we go here and we see that there's a new argument to the next function. It's a for each argument. What's the for each argument does? Well, it takes as input a list you see here. And if you know word2vec, this is hyperparameters. So these are different versions of the model that we can train, okay? And once we do this, Metaflow is gonna execute the training function one time for each of the hyperparameter configuration. In this case, there are 3 hyperparameter configuration. So we're gonna get 3 different models here, right? And
as we know, a picture is worth 1,000 lines of code. If you can scroll up and just go to it will exactly. This is exactly what's happening. Yeah.
Exactly. So for each parameter config, we're gonna basically train a different models, and then we're gonna join them. We're gonna see the join runs here. You see here, the join run step takes all the things that we train. You see here. And it sorts, it figures out what is the best model, depending, okay, on the validation metrics, in this case on iterate, okay? And it's gonna store the final vectors, we call final vectors, as the best model for subsequent testing, okay? So we train 4 or 3 or 70 or how many you want. We check how well they're doing on the validation set. We pick the best one. And then in the model testing phase, we do a final evaluation on the iterate on the test set, okay? What is the test set evaluation for? Tested evaluation is your best proxy for how well the model generalized, because the test set has never been seen by anything before this point, okay? So it's very important that you use the test set before this point, because it will actually bias your evaluation, okay? So if you go again here, prepare the test, generate 4 different models or whatever you want, join them and find which one it is, and then do a final test to make sure that your model actually works. In a production setting, let's say you have an accuracy threshold for business reason. Like, let's say you don't want to deploy a model that is below 0.3 because of whatever business requirement. This is where you will put your check. So basically, you will put your check here, okay, and you will stop. You will alert the system. You do something here to avoid the model to go in production, okay? Still, any questions so far?
No, yeah, so there's one question with respect to the conversation before from Antonio. Would it make any sense to compress data when you have so much of it that are passed to the next steps, like converting with PyArrow or something like that?
Yeah, absolutely. Actually, you can totally do a PyArrow table. You can do anything you can do in Python, you can do here. Like, you're not in any way limited by what Jacopo, Hugo, and Eddie came up with for this. You can use whatever tool you want in Python, okay? And that's, I think, the beauty of Metaflow. Like, nobody's forcing you to pick a tool you don't like or you're not comfortable with. As long as it runs in Python, it basically will run here, okay? So you're free to experiment with whatever efficiency gain you can. My argument here is that even pretty vanilla things are freaking powerful. So the lesson for today is not in 300 lines of code you can run Netflix recommender system. That's not what we're going to teach. What we're teaching today is in 300 lines of code you get a baseline that is freaking awesome. Consider how straightforward it is to set it up. Okay, and then you can sky's the limit. Go and improve and make it better in so many possible ways.
Exactly. So just to foreshadow what's happening, we're near the end of the hour. But what we're going to do is analyze the results now, and then we're actually going to deploy an endpoint and make real-time predictions.
Exactly. So we're gonna go notebook pretty quickly. But what is the remember all the time we self-stamping in the flow, right? Remember that as Hugo and myself said, we version that, we store them in the meta store. Okay, this is come in handy because every time you have finished training, okay, just by knowing the name of your flow, okay, look at this. This is the same one as the flow class that we have. We can actually retrieve the last successful run, and we can retrieve the model and the data set that was trained into that without any additional tool, okay, without any additional system or without any special setup, right? And that happens because of the self magic that basically version everything for you, okay? So in this case, let's say we're analyzing our result. Again, we train our first version. We have 3 different models. We pick the best one, and we want to see how well we're doing. So first, let's get back the dataset to make sure that we were training on the right dataset. And you can see here the exact representation that we saw before, okay? So we have a sequence of artists, the sequence of tracks, and then the distinction between the first N and the N+1 song in a playlist, which is going to be the test song, okay? But even more interesting, we can actually recover our vector, the last vector that we trained, okay? And then we can do a prediction, which is offline, it's just on our notebook, by comparing, you know, a track that we like, let's say in this case is this one, to the most similar one in the space. Again, remember the intuition here, a track is a good suggestion if it's close in the space to a track that we just listened to, okay? And so we can get, you know, any sort of prediction here. So if you run this again, since there's a randomized component here, you're gonna get a different suggestion. Okay. We're not gonna go so much into the details, but one thing that I want to share is the Hugo battery problem in the song version here. You see here, so this is one of the most common song in this data set, right? When you actually do the prediction, what do you see here? That the second song is basically, sorry, the first song is basically the same song, just without radio edit, okay? Which means that it's basically a duplicate, okay? So on one side, this is bad. It means that 2 songs which should be really the same song are not represented as such in our data set, okay? This will make the problem even more challenging. On the flip side though, how cool is it? Like the model, without knowing anything about Daft Punk, Get Lucky, without actually even reading this, is actually able to find out that these things are so similar just based on the pattern of usage, right? The model basically is a deduplication model by itself, just because it's so good at distinguishing which songs are similar to each other. So bad news for our data set. Our data is dirty, and this analysis reveals it. But good news about our model is actually very powerful. So should we deploy?
I am so excited to deploy.
Okay, let's close it up. Let's close our loop. You know, we promise end-to-end, we're gonna do end-to-end. So
exactly.
Let's say our analysis has made us happy. We made whatever modification to the data set, to the model we want. We're ready to run the full flow. So this flow here is the very, very, very full flow with all the comments. Like this is a much more verbose version of that because it's the actual full story, okay? So you are encouraged to go through it at your own pace after this. But let's run it because we want to generate predictions at the very end. So what's gonna happen here is that we're gonna do exactly as we did so far, okay? With the training. So we're gonna train models, we're gonna pick the best one, and we're gonna serialize it. And then we're gonna spin up in this sandbox, thanks to the magic of Eddie and Hugo. We're gonna use TensorFlow serving to actually serve prediction. So we're gonna actually put this model into a server, and then we're gonna query it with another Python package, okay? And we're gonna see how responsive it is, okay? And this will basically simulate, let's say 90% of a real deployment, okay? And it's gonna show you that the model that we trained today can be put live in front of user, okay? And what's gonna happen live? Well, you give the model, a song, and the model is gonna tell you what to listen next, Okay, so we're gonna see our recommender system comes to life in some sense as a live system, not just as a training loop. Okay, so let's finish it up while he's training. Okay, almost done. We're testing the model to make sure that everything is fine. Okay, iterate on the testing set, and now we're gonna do the last part, which is moving this model into a Keras model, which is a trick so that we can use the Keras embeddings to perform the KNN similarity judgment that we need in real time. Okay,
Great.
And if you see here, you're gonna go. Do you see this line? You're gonna copy this line, and then we're gonna paste it here. Okay, and this is gonna set up our server, and then you can copy one of the prediction here, and you're gonna go to another terminal. You're gonna copy Python predict, and this is the result. Wow. Okay.
And so you've we've just literally set up an endpoint that you can ping in order to get your predictions based on this neural network sequential recommender system. Now you're doing this locally or in the sandbox, but that isn't the only way you can do this. This endpoint you can open up to anywhere and use in any application, essentially, right?
Yes, exactly. So if you go in the live version of this, live as in the one on the website, you're gonna see that the Keras model that we use to do this, fast KNN search, which again is a fancy word for giving the most similar song to the one that I just gave you. Okay, can be just embedded into SageMaker. So, for example, if you use a cloud PaaS solution like SageMaker in AWS, you can ship the exact same model, and it's going to be available to anybody in auto scaling and massive scale in the cloud without you having to worry about any maintenance on infrastructure. Okay, if you're following up until now, this model here will work in your sandbox, and you can actually query, as I'm doing it now. You can actually query with whatever song you want, right? For example, you can change the script that we provide here, and it's going to produce new recommendation into that sense, right? So
fantastic.
Works end to end.
And we have a great question from Antonio De Luca. Jacopo, what do you think of using MLflow as an experiment tracking database aside of Metaflow? I see it as pretty handy to compare a bunch of different experiments. Before you answer that, I'll give my answer. I mean, the Metaflow interoperates with all types of different tools. And so if you use weights and biases or MLflow or Neptune or Comet or whatever it is, all of these things can be used with Metaflow. And we encourage you to use whatever you find easiest and whatever your organization uses as well. So that's kind of my Metaflow-esque answer to that question. But Jacopo himself may have different.
Well, I mean, that's nothing to add. If you look at other collaboration between my team and Outerbounds, you're gonna see different repos. They're all open source, different ways to integrate exactly all the fantastic tool that Hugo mentioned, Neptune, Comet, weights and biases. So there's just the ecosystem is full of great tools, and I think the Python first approach in Metaflow as compared to other philosophy actually kind of encourage you to go and improve on flows by adding these tools on top to improve monitoring, observability, and all of that.
Yeah, and actually, would you mind going to your second tab, the one recommender system? Oh, sorry, no, in Chrome.
Oh, sorry, yeah. Oh, sorry, yeah, sure.
And if you scroll down on the left hand to how-to guides. Now, if you go to versioning on the left-hand panel and scroll down, you'll see, for example, use weights and biases, right? So if you scroll down, you'll see this is how Metaflow can be interoperated with weights and biases. And so we have a lot of how-tos on how to do these types of things, essentially. All the types of things you will want to do with Metaflow and other packages and other frameworks, for example. So let us know. I put the link to our Slack. If there are questions you have and things you'd like to see here, please let us know. We love making these things. I want to give a huge shout out to Eddie Mattia, our colleague and friend who builds all of these guides. And also to our fabulous designer, Gaurav, who, I mean, the way this page is structured, I love having that code on the right, the execution on the left. It's very beautiful. So this whole thing is a huge team effort, along with all the engineers who build the work on Metaflow as well. So anyway, the point is that we want you to be able to use whatever you like to use, and those how-to guides, for example, are a place where you can find out a lot more about that information. Shameless plug. So we have one more question. Can you go over the deployment again, if you don't mind? One way I can think of doing it is run the Metaflow client, how TensorFlow serving point got created. The end step in the last notebook or in the last script has print statements only. It was not clear quite what is happening. And in fact, we have another question that I'll answer in the chat is the code open source GitHub? And the answer is yes. I'll link to the GitHub repository.
Yes. So yes. So this is the local endpoint that we're doing here is for again to show this into the sandbox, because we didn't want you to have a AWS SageMaker account to run this as compared to to our normal flow. If I can go to the, I think it's yes. If I can go here back. If you go into the actual full-fledged flow, which is here, you're gonna see the deploy function that is very explicit. So the retrieval model is basically the same, but the deploy function is gonna actually use Boto3 and SageMaker. Is gonna create a TensorFlow model and is gonna deploy the model that we train. Okay, which shows a few things. SageMaker has pros and cons, but it allows you to have a very clear, very somehow declarative approach to create resources in Python, as compared, for example, to sub-processes or things you need to run by knowing other processes, like we're doing in the demo. And the second thing is that how easy it is for you to take, in this case, the path of the model. So SageMaker takes as input where the model is stored on S3, which again, thanks to Metaflow, everything in S3 already, okay? And then deploy it with whatever hardware you want, okay? This is also a very Metaflow thing philosophically, even if this is SageMaker, that is, the code is one thing and hardware is somehow a variable, a configuration that you can kind of swap in and out. So you can run this code with very different hardware for SageMaker if you want, or even different, instance counts if you want to deploy it, on horizontally, and the code is going to be the same. Like the same code can generate an infinite amount of deployment, so to speak, just because the business logic and the implementation are somehow kept separate by design, which I think is one of the great insights of Metaflow in general. So if you're interested in the full deployment, I will totally suggest you to go into the SageMaker version into the official website.
Yeah, which I've linked to in the chat. We actually have a whole slew of more interesting questions coming in. We can't get to them now, unfortunately. But what I would love for you all to do is to come and chat with us on Slack about them. So I've just put the link. Join us on our Slack workspace. We've got thousands of Metaflow users and data scientists discussing questions just like this. I do also want to give a shameless plug. And this is something that I think, a lot of you will be interested in. Later this month, in a couple of weeks, we have a fireside chat about natural language processing from prototype to production with Ines Montani from Spacey and Explosion AI. So we'll be talking about these types of things, but with a serious bent on NLP, which is also Jacopo's home turf. So I'm just putting a link to that in the chat. There were so many great questions, and we look forward to chatting about the rest of them in Slack. Jacopo, are there any last thoughts or words you have?
No, I mean, thanks so much for spending the time together. Hope it was just not insightful, but also fun and kind of easy to follow. Thanks God we're not falling off the face of the earth. So if you need any question, reach out on the Outerbounds Slack. We're always there, and we're happy to continue the discussion or even go into do some deeper dive into some aspect that, of course, we couldn't go into because of the time. But if you have time to go through the flow yourself, and in 1 week from now you find out there's a question that you really want to ask, please do. Again, this is a continuous conversation. We have one event, and we have, of course, you have to have boundaries. But after that, we can continue chatting about this. And super happy to share also my production experience with Metaflow, one-on-one if you want to reach me in personal messages.
Absolutely. So I'd just like to thank everyone for joining and sticking around. So great to have you here. And thank you, Jacopo, as always, for giving us your time, but also it's such a joy to chat with you always. I always learn from you, and to do this type of stuff is not only incredibly informative, but it's a lot of fun as well. So thank you for making the world of building recommendation systems fun also.
Thanks for having me, guys.
All right. Ciao, everyone.
Ciao.
And